Hello, this is our third video in Module 1 on structure and bonding. Picking up where we left off, we saw sp3 hybridization leading to essentially a carbon with 4 single bonds. That describes the bonding in this molecule ethane. Below is a picture of the orbitals where they're each bonded to hydrogens. Notice these are covalent bonds because they are shared pairs of electrons, one contributed by carbon, one by hydrogen. The hydrogens are basically 1s, 1 orbitals, as you recall. So let's take a look at some of this. The formation of ethane, if it was to proceed this way, these are all sp3 hybrid orbitals from the 2 carbons. And now it just brings in the hydrogens, 6 of them. So each carbon has 4 bonds. Just showing you the tetrahedral geometry is preserved throughout the molecule. And it's going to show you the space-filling electron distribution map, where the red is higher electron density. Now, experiments show that this molecule ethane can be made from a simpler molecule with the molecular formula C2H4. Using this reaction shown here, C2H4 with hydrogen gas bubbling through it in the presence of a metal catalyst like platinum or palladium will give you the above molecule ethane. So that's determined experimentally. The question is, what is the molecule C2H4 and what is its structure and geometry? You can take a look at this reaction. It's getting ahead in figure 8.5 in McMurray if you're interested. It's kind of interesting. So the molecule C2H4 is called ethene. It has a double bond, which explains its geometry. How do we explain the bonding for this? Using hybridization theory. So we'll maintain that the 1s2 is buried deeply inside, closer to the nucleus. In this case, to explain the structure and bonding of ethene, we hybridize one of the s orbitals and 2 of the p atomic orbitals, and we leave off the remaining p atomic orbital. That gives us 1, 2, 3 sp2 hybrid orbitals. Okay, and then it leaves a p orbital unhybridized. If we draw a picture of this, below here we see, already drawn, here's a carbon center. It has 1, 2, 3 sp2 hybrid orbitals, and in a right angle plane to those is the unhybridized p orbital. We still have our 1, 2, 3, 4 carbon electrons to fill in. So the unhybridized p orbital does still have an electron in it. The other carbon of ethene also has an unhybridized p orbital with an electron in it. These will end up overlapping. They're closer than they appear in the picture here. They overlap to form a pi, what we call a pi bond. So what we end up as an orbital and bonding picture of ethene is 3 single bonds from each carbon. These are the 3 sp2 hybrid orbitals, shared pairs of electrons in each, and the pi bond, which once the pi bond orbitals overlap, they create a picture that looks a little bit more like this below. As you see, I'm circling. So we don't draw this every time we want to talk about ethene. We draw this. So we use a lot of symbolism. And the interesting thing here to point out is that notice we draw the double bond, as we call it, as two lines, but the orbital picture clearly shows that one of the lines is a sigma bond. The other line is the resulting pi bond. I could have drawn them either way, up or down, switched here. So this is completely symbolism. But when an organic chemist sees this, they think the picture above, or any of these other pictures. The reason this is so important is that if we look over here, this pair of electrons that constitutes the pi bond is reactive. Those electrons are sitting above and below the trigonal planar geometrical plane of the molecule. So they're sort of sticking out above and below, and therefore reactive. They represent regions of high electron density. So we can take another look at this. So here's our sp2 hybrid orbital formation. Here comes the s orbital and two p orbitals. So sp2 is simply an s and two p's hybridized into three sp2 hybrid orbitals with trigonal planar geometry. Now, the molecule ethene that we just showed has the two carbons already hybridized in that way. The yellow orbitals on each are the unhybridized p orbitals. You see them overlap to form the pi bonds. So we have a pi bond above and below. The green are the sigma bonds, all sp2 hybrid orbitals. The four hydrogens are attached. The side view is a little bit more informative. And then there's our electron density map. Notice the high electron density above and below, red colored. That's what I was just talking about with those electrons in the pi reactive pi orbital. All right, so moving on to explain other forms of bonding. Really, this is so a logical progression of where we are now is sp hybrid orbitals. We've already shown what happens when we take an s and three p's and overlap them to give four sp3 orbitals. We saw what happens when we take an s and two p's and overlap them, hybridize them, I should say, to form sp2 orbitals. What if we take an s and a p orbital only, leaving two p orbitals unhybridized? Then we get two sp hybrid orbitals and two unhybridized orbitals, p orbitals. I've already drawn what that ought to look like. Each carbon having an electron in each of its sp hybrid orbitals. So sp hybrid orbital, linear geometry. Unhybridized p orbitals, each with an electron in it. Then you'll have overlap created there to form a pi bond, and overlap there into there to form another pi bond, so you have two pi bonds. So there's a linear sigma bond framework and two additional pi bonds, and we can represent it in a similar way with the two carbons and 1, 2, 3 bonds, we call it a triple bond. But just like before, only one of those is a single bond, sigma bond. The other two are pi bonds at right angles to each other. A little difficult to draw, but we can show, again, sp hybrid orbital formation. So here's an s orbital, and just one p orbital. Hybridize it. We have a linear two sp hybrid orbitals, one above, one below, shown there. If we show the molecule ethene as it forms, so if it was to form this way, so you see the linear sigma bond framework in green, the pi bonds above and below and coming toward and away from you. Here come the hydrogens. Now we should see high electron density sort of all around the waist, the middle of this molecule, once we get to that part. And there it is, that high electron density around the middle. Okay. This is a little bit longer video. Few conclusions here. We have the upshot of all of this. sp3 hybrid orbitals, 4 of them, lead to 4 single bonds around carbon and a tetrahedral geometry. sp2 hybrid orbitals, 3 of them, lead to a double bond and trigonal planar geometry. 2 sp hybrid orbitals lead to triple bonds and linear geometry. So, doing a little bit of a deeper dive here, if you have an sp3 hybrid orbital, or 4 of them as the case is usually, think about that. It's 1/4 s, 3/4 p. So it has much more p character than s character. P orbitals are more elongated. So an sp3 hybrid orbital might look like here, where the nucleus maybe could be represented there. sp2 hybrid orbitals have more s character relative, still 66% or 2/3 p, right? But having more s character means it's more spherical, like more s, it's more s-ish, right? So nucleus here, more spherical orbital. sp, there you got a 50-50 mix. And so it's even more spherical, more rounded, say with the nucleus here. So the interesting thing is, remember the nucleus has the plus charge of the protons. Whatever's over here that this atom is interacting with feels less of that plus charge in this uppercase than in this, say, lowercase for sp hybrid orbitals. Notice it's closer in distance here to the nucleus. So this particle or other atom or whatever it is feeling more plus charge, quote unquote, feels more plus charge. And so we can conclude that sp hybridized carbons are more electronegative. It's a very interesting result of all of this. So carbon compounds with triple bonds behave in that way, and we won't see that until we do a lot more reaction chemistry later. But essentially, the take-home conclusion here is that hybridization theory, all of this, strongly affects things like bond length, which we just saw, bond strength, geometry, and reactivity. And the main big conclusion stays the same. Structure relates to function.